I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for these students, this class. Just pray that you be glorified in what we do, and that we all understand a little bit more about vectors today, Lord. In your name I pray, Lord Jesus. Amen. So I'll get straight into it. Let us talk about vectors, how to add them, dot products, and all that. I want to share with you guys, notation, which makes these things much easier. So let's get straight into it. So what is a vector? So primarily we're talking about vectors in 3 dimensions in here, right? So like a vector is, we can write it this way, right? Or if you like, you could write that as like A1 like this, right? And so the notation that Griffiths uses, and I will use as well, is that this is x hat, this is y hat, and this is z hat, all right? Or sometimes if I like to enumerate things, I'll call this x1 hat, x2 hat, and x3 hat, right? These are unit vectors respectively in the xyz or x1, x2, x3 direction, right? So the point then is that we can build any vector as a sum of its vector components, right? Which is super nice. All right. Now, and then of course you can talk about addition of vectors, right? Like, and I won't belabor this, but like here was the definition of vector addition is like this, right? Definition of scalar multiplication like this. So there we go. That's how we add vectors. That's how we scalar multiply. But we should introduce the dot and the cross products, right? So the dot product is defined as such: A dot B equals to the sum of A sub I, B sub I, right? This is the dot product. Now, one of the fundamental things we should notice, of course, is that if we have x hat sub I and we dot it with x hat sub j, we get what? We get what's called the Kronecker delta ij, right? So this thing is 1 if I is equal to j, it's 0 otherwise, right? So this is the, and what this expresses, of course, is that the Cartesian, it's okay, sorry, it's back there. Whatchamacallit? This is the orthonormality, right? They're perpendicular and they also have length 1. Now, length 1, I guess that's not clear yet. What's the length of a vector? Well, length of a vector, as you guys know, we just take the vector and drop the vector symbol for the magnitude, right? In terms of the dot product, this is naturally defined to be the square root of A dot A, right? So that's how we can write magnitude in terms of dot products like that. And of course, any vector, if A is not equal to 0, right, then A hat is equal to 1 over A times A, right? This is the unit vector in the A direction. And this quickly gives us that any vector can be written as a product of its magnitude and its direction, right? This is a very nice thing to know about. We use this all the time. Now, what are the properties of the dot product, right? Let's think about that. So, of course, one of the big ones is that it's commutative, right? It's also distributive. We can pull constants out, right? I'm not even going to write that down. That's not that interesting. I don't know. Is there anything else? I guess that's... What else would I say? I think that may be positive definite. Yeah, I guess that's... Yeah, why not? Let's throw that in for good measure. What Sam is getting at is that A dot A is equal to 0 if and only if A is equal to 0. So in that sense, yeah. It's like the dot product of a vector with itself is 0. Because the dot product vector with itself being 0 means that the length squared is 0, right? And the only way the vector length squared can be 0 is if the vector is the 0 vector. All right. Now this is not a math class, obviously, right? This is Physics 331, but it's important for us to kind of just review Calculus 3 as a starting point, because we're going to be using Calculus 3 to describe physics this semester, right? So that's why I'm doing what I'm doing, if you're wondering. Okay, so next, cross product. I am resisting the urge to prove these things, right? Which we could easily do with this notation in all of about 30 seconds. But I'm not doing that. I'm trying very hard not to do that. I will save my proofs for when we actually get something a little more substantial, like this maybe. So the cross product, here's something maybe you didn't see in Calculus 3. The cross product can be written as the sum over I, j, and k equals 1 to 3 of epsilon I, j, k, a sub I, b sub j, x hat sub k. Now here, this is the so-called Levi-Civita symbol. So epsilon 1, 2, 3 equals epsilon 2, 3, 1 equals epsilon 3, 1, 2 equals to 1. On the other hand, epsilon 3, 2, 1 equals to epsilon 2, 1, 3 equals to epsilon 1, 3, 2 equals to minus 1. And epsilon I, j, k is equal to 0 otherwise. That's the definition of the Levi-Civita symbol, or the completely antisymmetric symbol in 3 dimensions. All right? And that folds into it the 6 non-trivial terms that form the cross product. 3 pluses, 3 minuses, it's all there, right? And this notation also elegantly allows us to express other truths. For example, x hat, x1 cross x hat 2 is equal to x hat 3, right? X hat 3 cross x hat 1 is equal to what? Right? X 2 cross x hat 3 is x hat 1, right? You might recognize these more if I used IJK or something, but this is the standard cross product relations, right? I can express all of these by simply saying that x hat I cross x hat j is equal to the sum over k of epsilon ijk x hat k. It's all there. See, because the only way that epsilon symbol could be non-trivial is if I, j, and k are distinct, which automatically forces whatever's on the right-hand side to be whatever's not on the left-hand side, which is exactly those patterns. Now, so this notation was not known to me as an undergraduate. I learned this in graduate school after writing like about 3 pages and then talking to my Spanish friend, Jorge, who's like, why are you doing it this way? Use the Levi-Civita symbol. I'm like, the what? And then I learned about why I had been cheated. Because all I did was study Stewart, which doesn't have this in there, at least not clearly or emphasized. But with this, you can do very nice things like prove, for example, here, like let's prove linearity of the cross product. Right? So we're talking about the sum over I, j, k, epsilon, I, j, k, a sub I, b plus c sub j. All right, let Let me save some writing here and just get to the point. What's the jth component of B plus C? It's what? It's B sub j plus C sub j, right? And then I put an x hat k over here. And then multiply and use properties of finite sums to rewrite it as two finite sums. The sum of sums is the sum of sums. It sounds like I didn't say anything, but I said something. I'm writing something anyway. And that's exactly A cross B plus A cross C. If you write this out using brute force notation, it takes a lot longer. And it doesn't really communicate why it's true any better than this does. Because this gets to the heart of the matter. The reason that the cross product is distributive is because real number multiplication is distributive, and the definition of the cross product is naturally fitting together with that notion, right? Like it captures the essence of why that's true. So this is index notation. Now physicists will oftentimes not write the x hat k here, and they'll just look at like the kth component and show the kth components of both sides are equal, and that's also fine. All right, I wanted to illustrate the method. Okay, so great. What are other properties of the cross product? Like, I think chief among them is what? A cross B is equal to what? How about this? Minus B cross A, right? Now, I won't prove this, but that's a straightforward consequence of the fact that the Levi-Civita symbol is built so that if you exchange any two indices, you get minus what you started with. That's why that's true. But anyway, this is true, of course, and this naturally leads to what? Any vector cross itself is what? 0, right? We know that. So, all right, these are the basics. What are like the sort of next level thinking in terms of dot products and cross products when we start talking about angles, right? So a big theorem is this, right? A dot B is equal to AB cosine of the angle between them, right? That theorem is logically equivalent to the law of cosines. Like I would prove this in Calculus 3 if you're interested. I'm just going to say it here, all right? But you can derive that formula from the law of cosines on a triangle with sides A and B, all right? On the other hand, A cross B, what's that? Well, the magnitude of it's what? It's what? AB what? Yeah, AB sine theta. Which is kind of a little bit disconcerting. Like sine can be positive or negative. Why don't we have to write absolute value here? Where's theta? It's from like 0 to 180, right? So sine's positive there, or 0. So that's why that's okay. And of course, you guys know the drill. A cross B, without the magnitude, it's what? It's, you know, AB sine theta n hat, where that's given by the right-hand rule, right? We know this. Great. So let me not try to, I don't want to bore you guys today with this stuff. I'm trying to get through this. All right. So this, this is also a theorem, not as easy to derive, you see. Why is it that the magnitude of A cross B is AB sine theta? That actually takes me a little bit of work to derive that in Calc 3. It rests on something called Lagrange's identity, which is not entirely easy to prove. But I must resist the urge to talk further about that here. So I should talk next, of course, about the triple product. What's that? So if we have A dot B cross C, right, that's the triple product. What's the significance of the triple product? Yeah? The volume of the parallel pipette. Now, when would Sam not be correct? It's flat. It's flat. Well, I would just say the parallel pipette has, you know, oh man, I'm trying to think of how to. I think if the picture looks something like this, I'm trying, guys. I really should have used some color coding, my bad. But if the picture looks something like that, Sam would be right. Well, that's what we said. You know, I've got complaints on YouTube before for chewing gum during videos. I wonder what kind of complaints I'm going to get for eating a watermelon during lecturing. What do you think? Anyway, so it has to be the case that if we take the cross product of A and B, C has to be, like, the cross product of A and B, it doesn't have to be the same direction as C, but it has to be on the same plane, same side of the plane with normal defined by A cross B, right? Like, if I take A cross B and C is kind of in the same general direction, then this actually is the volume of that parallel pipette. On the other hand, if I took, you know, A cross B and it was like downward and C was upward, then this would be minus the volume because the triple product would be negative. There are various ways to calculate this. One really nice thing to know, of course, is that this is the determinant of A, B, C, like that, right? It turns out. And because the determinant has super awesome properties, like this is also, you can do this, and you can do this, right? And so this is, by the way, B dot A cross C, and this is C dot A cross B, right? So the fact that the triple product is equal to these cyclic interchanges of the letters, like this and that, these all three are equal, it's called the cyclicity of the triple product. All right. This is at times useful to know about. Like, here's a theorem that I haven't tried to prove. I wanted to have time to work this out before class, so what I'm about to do is very dangerous because I have no earthly idea how hard this is to prove. But we should try to work out something together, right? At least in this material. But really your main job at the moment is to read chapter 1 in Griffiths and just kind of like refresh your calculus 3 basic stuff and get used to his notation a little bit, because his notation, of course, is a little bit different than Stewart or whatever you were using. I mean, if you had my calculus 3, it's more like this because I was raised by physicists, you know, at least in terms of Calc 3. But here's my proposition for you guys. Suppose we have 3 vectors, right? So I'm going to claim this. I'm going to make a claim. All right. If we have U1, U2, and U3 with UI dot UJ equals to Kronecker delta IJ, right? And U1 cross U2 is equal to U3, then we get 2 things. We get U2 cross U3 is equal to U1, and we also get U3 cross U1 is equal to U2 necessarily from this data. Now, at this point, I feel like I'm in a physics class and there are things I have to do in here because we're in a physics class. And one of those things we have to do is draw vectors on vectors. Otherwise, it's very bad. So, hat, 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 hat. There we go. These are unit vectors after all. That's reasonable because notice that if we put I equals to j, we get like ui dot ui is 1, which says that the length of ui is 1, right? So what is this in words? This means that the set u1, u2, and u3 is, you know, pairwise, perpendicular, perpendicular pairwise, and what else? Length 1, right? So in mathematics, we have a nice simple word for that. That's orthonormal. And also in physics, right? Physicists use the word orthonormal as well. So it's an orthonormal set. So what do you guys think? How are we going to get from there to there? I think we might need to pull another rabbit out of our hat that you guys are going to prove in your homework. So let's make use of your future work. All right, so like one of your homework problems, like the first interesting one perhaps, is to show that the cross product is not associative. So like if somebody writes A cross B cross C, that's a quick way of them telling you they don't know what they're doing, right? But one of the things in your homework you're going to do is show that A cross B cross C, right, is not equal to A cross B cross C generally. All right, that's one of the things you're going to explore in your homework. And part of the way you're going to do that, part of that problem involves proving what's called the back cab identity. So A cross B cross C, right? So the a cross product of three vectors like this. It turns out, and this is in like the front cover of Griffiths, right? He writes it back cab. So he writes B times A dot C minus C times A dot B. Now I don't usually write it that way because as in mathematics we don't usually write scalar multiples on the right. All right, so like in my homework problem, I think this looks like A dot C times B vector minus A dot B times the C vector. So that's mine's no longer the back cab identity, it's the ABC identity, I guess. But it's not at all, this is not by any stretch of the imagination an easy thing to prove. This is quite horrible unless you use my hint in the homework. Do use my hint. Otherwise it's much suffering. But if you use this, you can easily prove that the cross product satisfies something called the Jacobi identity. So like it is true, well this is not true, it is true that A cross B cross C plus B cross C cross A plus C cross A cross B is equal to 0, adorned with the appropriate vectors and parentheses. So this altogether is one of the things you'll show in the homework. This is called the Jacobi identity. This is an interesting identity. It shows that if we take the three-dimensional space and pair it with a cross product, it forms what's called a Lie algebra. Lie algebra is a space that allows for addition and multiplication, which is not associative, but almost associative. This is the departure from associativity it has to satisfy. And this is interesting to physics because Lie algebras are at the heart of modern physics, right? So as a physics student, something you want to learn about eventually. And this is the first example, kind of interesting example of a Lie algebra, just the cross product in R3. But to prove this, it's pretty easy if you use the back cab identity, because you can just replace each one of these with these guys, and then you can use like properties, like commuting properties, the dot product, and cancel things out. I'm sorry, I'm going to stop doing your homework, but it's not bad if you do that. It is bad if you ignore the hint. Now, my fuzzy intuition is that we can use this technology to prove my claim. What do you guys think? I don't know. Maybe, maybe not. There's one other theorem I need to share with you guys. And this is kind of more like either geometry or linear algebra, however you want to look at it. If we have three vectors in 3 dimensions, right? And they're pairwise perpendicular in length 1, that means they form a basis for 3-dimensional vectors, right? That means any vector can be written as a linear combination of these 3 vectors. Let me show you how. If we have V is equal to a sum of like Ci ui hat, then, well, let me say this theorem a different way. If V is a vector given v in R3 like vector, then v is equal to this with ci equal to v dot ui hat. All right. I mean, how do you prove this? It's like not. If I take, oh man. If I take v, nowhere close. If I take v, if I take v, seriously, I'm getting worse. All right. If I take v, okay, I can live. So it looked like v dot uj hat, right, is equal to the sum I equals 1 to 3 of c sub I. I guess I have to assume that I can write v as a linear combination of these, and perhaps that's linear algebra, but you'll forgive me if I don't do everything here today in class. I'll feel guilty about it and write better notes after the fact. I'm sorry I ran out of time. But if we do that, right, what happens here? Yeah, Ci, Kronecker delta ij, which then that just collapses down to Cj, right? And then that proves this theorem, which is to say that if you have an orthonormal set of vectors, you can build any vector as a linear combination of those. And not just that, but the coefficients that you need to build the linear combination are found by dot products. You're most familiar with this in Calc 3 in terms of the fact that like any vector, right, if I have like vector v, I can write it as, you know, v dot x hat, comma v dot y hat, comma v dot z hat, right? If I want to calculate the x and the y and the z components, I can select those by simply taking the dot product of the vector with the unit vectors. Well, this is still true for an arbitrary triple. Yeah. And uh-oh. So my suspicion is that if we use that, maybe we can prove the claim. What do you guys think? Could be. So like let's take, for example, we want to calculate like U2 hat cross U3, right? This, by my general basis theorem there, it has to be U2 cross U3, right? Dot U1 plus U2 cross U3 dot U2. I'm an idiot. What am I missing? Oh, goodness gracious. Times what? So that's the component, but I have to put it in the U1 hat direction. I have to, there's the U2 component and the U2 hat direction. Sorry, I thought this would be more interesting. I warned you I hadn't worked it out beforehand. This is one of those consequences of getting assigned this course a week ago. But, you know, it'll get better. Promise. Empty promises. But look, so that's just the, you know, any vector can be written as a linear combination of the U1, the U2, the U3 components if this is a basis, right? But what can we do with these guys? We could use the cyclicity of the triple product, right? Like what happens here, this is the same as what? Like U2 cross U2 hat, right? Dot U3, right? And this one, we can use the cyclicity of the triple product to rewrite that as U3 cross U3, right? Dot U2. But that is 0, that is 0. And how about this? because it's a cross product of the vector itself. We're assuming that u2 cross u3 is given to be u1. So we got u1 dot u1, u1. Oh, what have I done? Oh man, yeah, sorry. Thank you. You know, it's really easy to do a proof if you're assuming what you're trying to prove. It's usually true. Don't tell Dr. Sperano. Let's see here. So then, how about this? Maybe we should use the cyclicity of trace to push this over and pull that back. So that would give us u1 cross u2 dot u3 u1, right? Then this, we are given, is u3. But this is 1, so we've got u1, which is what we're trying to prove, right? And the proof of the other assertion is very similar. Again, you could just expand and use the cyclicity of the trace to see that this automatically follows. This is really nice because we're going to look at some coordinate systems other than the Cartesian coordinate system, and we'd like to know that this pattern holds, right? Like if you want to check that you have a right-handed triple, namely that you've got these patterns that I've only partly erased, right? This is a right-handed triple. The cross product of the first two is the third. The cross product of the third with the first is the second. The cross product of the second with the third is the first. This forms a right-handed triple, right? We'd like to know, it's kind of cool, it suffices to check one of those relations. The other two automatically follow from the cyclicity of the triple product. Yep.
You could also prove that with the norms. So you could evaluate the norm of the u2 cross u3. So you know the norm of both sides is equal and it's in the u1 direction. So then you know it's length 1, basically. Using the a cross b as a data.
Cool. Yeah, depending on how much we know, there's other ways. But yes. Okay, so anyway, let's move on. Now, we're really more interested in vector fields in here, right? So we're going to find ourselves doing calculus. And I will eventually decide where I'm going to erase. I think I'm going to erase here. So one of the things I loved about Griffiths, taking this course out of Griffiths, is I opened the cover of this book and all of a sudden there's this whole wild world of vector calculus that was before hidden to me in my calculus book that had 1,000 pages, you know? Like, there's all these dot product identities. I mean, most of those are in the calculus book, right? But this thing, that's harder to find. And all right. So enter nabla. So what is nabla? Nabla is x hat partial x plus y hat partial y plus z hat partial z. Now, probably to be fair, I should put a vector over that to be consistent with his bold notation. I'm not going to do it. It gets to be annoying in the notes and it looks bad. I'm going to write it without the vector. My apologies. But there's no danger of confusion. There is no scalar nabla. All right. So it's not too bad. But if we have nabla acting on a function, we get x hat partial x plus y hat partial y plus z hat partial z. Right? Or if we wanted to be civilized human beings, we could write the sum I partial x sub I hat, right? Or even more civil, the sum over I partial I f x hat sub I. There's an even better notation that's less writing, right? So this is the gradient. You guys have studied this before, right? In order for this to make sense, what do we need to know? F is a what? A scalar function, right? A function from R3 to, it could be temperature, voltage, something like that, right? We can also talk about the divergence. And we will. What's the divergence? So del dot, a vector field F, let's say, is the sum I equals 1 to 3. Sometimes I don't write I equals 1 to 3, but all the sums are from 1 to 3, okay? So my apologies if I'm shorting you some, ranges. But this is just partial f sub I, partial x sub I, or more briefly, the sum over I of partial I fi, right? So the divergence of a vector field is itself a scalar function, right? And in Calculus 3, we studied what that meant geometrically. But we'll get back into that in here before long. Curl del cross f. All right. By the way, you could, if you wanted to, you could write this. I don't know why you want to, but if you wanted to, you could see a Kronecker delta here, right? I don't know why you want to do that, but if you wanted to see a Kronecker delta there, you could. Just saying. Dot products kind of go to the Kronecker delta. The cross product goes to the Levi-Civita. So here we go. Sum I, j, k, epsilon I, j, k, partial I, fj, x hat k. That's the curl in this notation, right? So, yeah, question? No? Okay. So let me take this notation for a drive. What if we have the curl of like a scalar function times f? How would that work? Right? And what would happen there? So that's just the definition so far. But we have a derivative, right? This is a derivative of a product. So we do what? Product rule, right? So this is partial I g times fj plus g times partial I fj, right? That's the product rule. But put that up in there, and we get two sums, right? We get the sum ijk, epsilon ijk. I'll pull partial ig fj x hat k plus the sum ijk, epsilon ijk. Pull the g out, and we have partial I fj x hat k. So let me point out that we could take this g, right? It's got no I or j dependence. Let me just pull it out here, right? Because it's got no I or j dependence, so it just pulls out like that. And this right here, you should recognize what that is. That is the curl, that's the gradient of g, right? The ith component of that. That's what that is. So what are we looking at? Well, what we're looking at here is the curl of the gradient of g with f, right? Plus what? Plus g times the curl of f. And so that is a product rule for the curl. If you use the brute force notation, it's like a page, right? Because every one of these curls has got like 6 non-trivial terms to sort through. Now, if you look at Griffith's solution that's freely available online for any edition of his book that he's put out, I looked, it took me all of like 5 minutes to find the instructor's solution manual to Griffith's. I think he just does like the 1, 2 component. It's like, oh, 2 and 3 are the same. Well, that's cheating. This is the full argument, right? And you could prove similar product rules for the gradient and for the divergence using similar arguments. And at every one of them, the reason that there's a product rule for the curl, for the gradient, the curl, and the divergence is just because there's a product rule for partial derivatives. And that naturally interfaces with the definition of divergence and gradient and curl. And those product rules are all in the front cover of the book. Although there are deeper product rules, like the divergence of a the gradient of a dot product. If you look at that formula, it is got 4 terms, and it's got weird stuff in it. Like, it's got like a vector of operators. It's got weird stuff that you don't see in Calculus 3. And I'm not sure that that formula even matters anywhere in the book. I don't know if it even... mental note, does this formula matter? Or is it just like there to like impress or something? I don't know. But like the divergence of the curl of 2 vectors, it's essentially the same calculation as the back cab identity, but instead of, it involves, it's a combination of the back cab calculation and what we're doing here. So I might do that like next class or something, I guess. Or I might have some sense and go on. So I need to talk to you guys. And I'm going to go a little bit over today since we started so late. I'm sorry. But I'm trying not to go too far over. What time is it? So if you guys could, like, when it gets to be 5:20, stop me. All right? So I don't have my phone with me today, so I've got no, watch. But in the time that remains, I want to talk to you guys about the other coordinate systems that we use in physics. All right? So, like, one of the main potential confusions is that the spherical coordinates that Griffiths uses are not aligning with the spherical coordinates that, you find in math books. All right, so let's talk about that. Uh-oh. I never moved the camera. Oh, man. Oh, well. Huh. I guess I need to make one of you guys cameraman. Oh, well. Too late for today. What's that?
Someone's going to be cameraman.
Oh, okay. So, let's talk about physics sphericals. So here is so we, typically this is how we draw the XYZ coordinate system. That's still the same, fortunately. At least physicists haven't decided to like typically go with a different setup for that, not usually, thankfully. But here's where it gets weird. So this point out here, all right, this angle from the positive x-axis is called phi. And this angle swept off the positive z-axis is called theta. And the distance from the origin out to here is called r. So r, the spherical radius, is the square root of x squared plus y squared plus z squared. All right? And x, by the way, is equal to r cosine phi, sine theta. Y is equal to r sine phi, sine theta. Hey, look, the formulas agree at y, just enough to get you confused. And then z is r cosine theta. Notice that these are not the standard Calc 3 formulas, and these are the ones we'll be using in here, all right? Now, so that's the just a word of caution about that, all right? Now, any vector can be written in terms of like the spherical coordinate frame. So if we take a point in space here, we can think about unit vectors that go in the r hat direction. So it's one unit in the increasing spherical radial direction. Or we could sweep down like this in the theta hat direction. Or the phi, the one that sweeps around the xy, that, I have trouble drawing all three at once, but you can imagine it kind of going into the board. It should be perpendicular to the other two, right? There's phi hat. Maybe you can envision it. R hat crossed into the theta hat gives me the phi hat, right? So r hat crossed into the theta hat gives me the phi hat, if you can see that. But what do we automatically know from that? Assuming that we know that they're a right-handed triple, which we could, I mean, I can give you formulas. For example, r hat is cosine phi, sine theta, sine phi, sine theta, cosine theta. That's r hat. All right. Phi hat, I also know phi hat is, goodness, I think it's minus sine phi, cosine phi, 0. Because it's, you know, you can kind of, you could move the phi hat down. These limitations of my artistry here. Maybe I should draw it more like this. It's like that, if you bring it down here. It should be pointing in the direction of increasing phi. It's parallel to the xy plane. That's its deal. So you could kind of check my formula, right? Because if you're down here and like phi is 0, you ought to be pointing like minus y hat. No, y hat, right? Not minus y hat. Phi, like here, phi hat points like this, right? All right, so I think that makes sense. We get, when phi is 0, this is 1, so we get 0, 1, 0. That matches this. That's a check on my formula. We get back to here, we're pointing in the negative x direction. When phi is pi over 2, like here on the y-axis, we've got minus 1, 0, 0, which kind of matches like, you know, this. Yeah. Okay, so geometrically, I think it's clear what I wrote in the red. And we could figure out how to calculate the missing one here. Like these two are fairly geometrically obvious. Like if you think about the definition of the coordinates, you can see these, right? Put r equal to 1 into the formulas. That moves this back to here, you know, which is a natural way to think of it. And so we could get the third one, the theta, by taking what? Like the cross product of the other two in the appropriate order. All right? So this is new, right? Thinking of vectors in terms of the spherical frame, this is new, but this is going to be incredibly useful because it's going to give us ways of calculating flux integrals for problems that involve spherical geometry with far greater ease than the parametric approach of Stewart. And there's also a corresponding cylindrical frame that we can use for cylindrical problems that will make our life much easier for problems with cylinders. Now, this begs the question though, like how do you set up a vector using these kinds of coordinates, right? And that's what we'll start with next time. It's like how do you take a vector and convert it into the spherical coordinate frame, you know? So we need all the formulas to do that, but it's something like this, right? If I have f is equal to, let's say, you know, a, b, c in the Cartesian coordinates, right? Then we can rewrite that as f is equal to like the r component r hat plus the, you know, well, I forget which one goes first. I'm rusty, guys. And I got the math notation on my brain is the problem. But this would be like the spherical formulation of the vector field. And to calculate these, what's fr going to be? It's going to be like f dot r hat. F theta, it's going to be f dot theta hat, right? F phi, we're going to calculate it from like f dot phi hat. And we'll see that there are special formulas that we can derive, although I probably won't derive them in here, I'll just state them for you guys, that we can calculate the divergence, the gradient, the curl in terms of the other coordinate systems. It's not as simple as just repeating the formulas because the reason being that these frames, they change from point to point. So we can't, it's not just the same as x hat, y hat, z hat. There's a coordinate dependence here that figures into the differentiation and all that. Yeah. Oh, thank you. And that's where we'll stop. So, sorry guys, I will try to start earlier so we can end more on time, but.